Today we're going to work with geometric sequences and series, and so I put together a quick vocabulary list for you of all of the terms that we've used so far in this unit. You should be comfortable with all of these terms and understanding the differences. If you have any questions about any of them, please let me know. So in a geometric sequence, the terms vary by a common ratio. So if we look at the sequence 1, 2, 4, 8, we know it's not arithmetic because there's not a common difference. And we know it's geometric because we are multiplying by something every time. Specifically, we're multiplying by 2. So if we were going to continue this table, obviously their first term is 1, the second term is 2, third term is 4, fourth is 8, then we would have 16. And in general, we would have 2 to the n minus 1. If we go ahead and graph these, all right, there we go. We can see that we have an increasing function that appears to be exponential. But there is a difference between geometric sequences and exponential functions. Because exponential functions, we have always called that common ratio a base. And in the exponential function, we knew that bases are always positive. But that's not true in sequences. Ratios, that R value, can be negative. The general formula for a geometric sequence is A sub n or T sub n is equal to A1 times R to the n minus 1. So if we look at the first example, the first thing you always want to do is identify your common ratio. So what are we multiplying by? What do we multiply negative 81 by to get to 27? Or 27 is multiplied by what to get to negative 9? The answer is negative 1/3. We don't say that we're dividing by 3. We say that we're multiplying by 1/3. Okay, because R is always what's being multiplied by. So then we can use this formula and say that A sub 8 is equal to A1, so negative 81, times our R value of negative 1/3 to the 8 minus 1, or 7th. Without a calculator, we need to remember that 81 is negative, so negative 81 is negative 3 to the 4th, or the opposite of 3 to the 4th. If we raise negative 1/3 to the 7th, we'll also get a negative answer, because it's an odd power. This will be 3 to the 7th. So the good news is that the negatives will cancel here and here, and we can use the properties of exponents to remember that our final answer would be 1 over 3 to the 3rd, which is 1 over 27. Now that we know the formula for geometric sequences, we can look at geometric series. And unlike arithmetic series, we consider both finite and infinite geometric series. So in a finite geometric series, S sub n is going to be equal to A1 times 1 minus R to the n, and all of that is over 1 minus R. In a geometric series that's infinite, we denoted S infinity, and it's equal to A1 over 1 minus R, as long as our R value is a fraction that's less than 1. So we say that the R value, the absolute value of R, is less than 1. The absolute value of r being less than 1 means that each term in the sequence is getting smaller. So eventually you start adding something that's getting closer and closer to 0. So the series itself will approach a certain value. If the r value is greater than 1, then each term is getting progressively larger, and the overall sum is then getting progressively larger. So now let's take a look at some examples. So in the first sequence, I'm going to blow this up a little bit so we have a little more space. We see that we go 1, 5, 25, 125, 625. And so we want to identify the common ratio. What are we multiplying by? The answer is 5. The general term is a sub n, and a1 is 1 times 5 to the n minus 1. Then we need to find S10. So that's 1 times 1 minus 5 to the 10th over 1 minus 5. And we will type that into a calculator to get this number. So 2,441,406. Now, since the r value is not less than 1, we say that S infinity does not exist. Second example, r equals 2. So a sub n is equal to 4 times 2 to the n minus 1. S10 is equal to 4 times 1 minus 2 to the 10th over 1 minus 2, which again we'll use a calculator for, and we get 4,092. And again, we check our r value is greater than 1, so S infinity does not exist. Next example, we are multiplying by negative 2. A sub n is 6 times negative 2 to the n minus 1. S10 is 6 times 1 minus negative 2 to the 10th over 1 minus negative 2. Be careful when you enter this into the calculator. You should get negative 2,046. Absolute value of r is still greater than 1, so S infinity does not exist. And we'll go down and look at the last example. This time our r value is equal to negative 1/3. So that's good news. The absolute value of that is less than 1, so we'll have an S infinity. A sub n is equal to negative 3 times negative 1/3 to the n minus 1. S10 is negative 3 times 1 minus negative 1/3 to the 10th over 1 minus negative 1/3. Again, be very cautious when you type that into the calculator, making sure that you put parentheses around all of those negatives. When you type that into the calculator and convert it to a fraction, you get negative 14,762 over 6,561. Let me know if you have questions about entering it into the calculator. And then S infinity, we can finally find, it's a1, so negative 3 over 1 minus negative 1/3, which is negative 3 divided by 4/3, which gives us negative 9/4. And that makes a little bit sense because over here at S10 as a decimal, this is negative 2.24996. And we know that negative 9/4 is negative 2.25. So we can see that the values are approaching one another. Now we can look at the geometric sequences and series in context. So a union contract specifies each worker will receive a 5% pay increase for each year for the next 30 years. And the starting salary is $20,000. And you want to know the person's total lifetime salary over a 30-year period, which means that we want to know the total, aka S, so the sum, S30, as opposed to what they would be paid in the 30th year, which would be A30. So we'll go ahead and use the formula. We'll plug in A1. Now the R value will be 1.05 because it's a pay increase. So you start with your 100% and you're paid 5% on top of that. To the 30th over 1 minus 1.05. We enter that into the calculator and we get $1,328,776.95 over the 30-year period. All right, let me know if you have any questions.